So at the end of the last video, we worked example 4 using method number 1, which we said was the easiest method. We were told that a wooden beam has a rectangular cross-section of height h and width w, so it looks like this. The strength of the beam is directly proportional to the width, so that means it's a constant times width, and the square of the height, so it's a constant times the width times the height squared. And the question says, what are the dimensions of the strongest beam? So we want to maximize this. That can be cut from a round log of diameter 20 inches. So that means the diagonal of that beam has to be 20 inches. So that gives us a constraint. We know that h squared plus w squared has to equal 20 squared, which gives us h squared plus w squared equals 400. So this is the function I'm optimizing. This is a constraint equation. If I solve that constraint equation for h, or h squared, and substitute, I get this function. We optimized this at the end of the last video. We also said if we wanted to, we could solve this for w. We'd have w equals a positive square root of 400 minus h squared. So that's this function. Now, we didn't optimize this function to find the answer, but I told you at the end of the last video, we should be able to get the same answer if we optimize this function rather than this one. So just in case you were one of the students that would prefer to optimize this function, I've decided to make this video so we're optimizing the second function instead. So we're going to use method number 2, where we optimize the strength as a function of the height rather than a strength as a function of the width. So we know that our strength is this, and our height is some number of inches, between 0 and 20 inches. So we've got that. In order to optimize that function, we need to find the critical values of this function. So we're differentiating with respect to h. I've written that square root as a 1/2 power. So this is my first function, and this is my second function. When I take the derivative, I have to use the product rule. So we'll have the derivative of the first. K is just a constant. So the derivative of that first function with respect to h is k times the derivative of h squared, which is 2h, times the second function undifferentiated, plus the derivative of the second function times the first. Now that second function has an inside function and an outside function, so we have to use the chain rule. The derivative of a function raised to the 1/2 is 1/2 of that function to the negative 1/2. Then we put the inside function back inside without changing anything at all. And then we multiply by the derivative of the inside by the chain rule. The derivative of 400 is 0. The derivative of negative h squared is negative 2h. So this is the derivative of the second, and we have to multiply by that first function, which is kh squared. And the 1/2 and the 2 reduce. So we end up with 2kh times 400 minus h squared to the 1/2. And then we've got a negative h times kh squared, so negative kh cubed. And this 400 minus h squared to the negative 1/2 can be written as a 400 h squared minus h squared to the positive 1/2 in the denominator. Now, we want this derivative to be equal to 0. So in order to do that, we can get a common denominator and then factor it. Or, I didn't think of this last time, I've got this minus this equals 0. I could just set this equal to that expression and solve for h. So we have 2kh times 400 minus h squared to the 1/2 equals kh cubed times the quantity 400 minus h squared to the 1/2. Now, if I multiply both sides by this 400 minus h squared to the 1/2, my work is a little bit messy now. I've got that square root times itself. On the left-hand side, we're going to have 2kh times 400 minus h squared. And then on the right-hand side, these are going to reduce, and we'll have kh cubed. If I distribute that 2kh, I have 800 kh. When I distribute there, and then 2kh times the negative h squared is negative 2kh cubed. And that's equal to kh cubed. And now if I subtract this from both sides, we have 800 hk minus 3kh cubed equals 0. And that's what needs to be 0 in order for us to have a critical value. The h values that cause this to be 0 are the critical values of s. So we can factor this. I'm going to factor out an h and a k. I have 800 minus 3h squared here. 800 times hk is my first term. Hk times negative 3h squared is the negative 3k h cubed. And that equals 0 when either hk equals 0 or when 800 minus 3h squared equals 0. Now k is a positive constant because we're assuming that that strength is positive. So h equals 0 is one critical value. And then the other one corresponds to 3h squared equaling 800. We divide both sides by 3, we get this, or h squared, or h equals plus or minus the square root of 800 divided by 3. And the square root of 800 divided by 3, well, it's the square root of 400 times 2, right? All divided by the square root of 3. And the square root of 400 is 20. So we've got plus or minus 20, then times the square root of 2 divided by the square root of 3. Now, if I rationalize that denominator, I'm going to have plus or minus 20. Square root of 2 times square root of 3 is square root of 6, and then we'll have a 3 in the denominator. So that's our h value that satisfies that equation, h equals 0 or h equals one of these, but we want h to be positive and we want h to be between 0 and 20. So the only h value in our feasible domain is h equals positive 20 times the square root of 6 over 3, which is approximately 16.3 inches. And I know that because I did the calculation already and I typed it into Desmos, so I saw that decimal approximation of that number. Now, that is an h value that causes the derivative to be 0. We would be wrong to assume that that value that causes the derivative to be 0 corresponds to a max. Remember, we're trying to maximize the strength. We don't want to accidentally minimize the strength, right? To make sure that this corresponds to a maximum and not a minimum, we've got some options. We can either take the second derivative of this function here, which is possible, it's just pretty involved, or we can make a sign chart for s prime of h. I think I'd rather make a sign chart, but if I'm making a sign chart, that means I probably want to get a common denominator for that s of h, or s prime of h. So I think I'll do that. S prime of h was equal to this 2kh times the quantity 400 minus h squared to the 1/2. And then we were subtracting kh cubed divided by 400 minus h squared also to the 1/2. And then we multiply by that 400 minus h squared to the 1/2 divided by itself here in order to get a common denominator. That way our common denominator is that 400 minus h squared to the 1/2. Then in the numerator, we're going to have 2kh, and that square root times that square root is just the expression inside. It's like taking the square root of x and multiplying by the square root of x. You get the square root of x squared, which is x, as long as x is positive. And this 400 minus h squared is positive on the interval of interest, so we're fine there. And then we subtract that. The denominators are the same, so we subtract the numerators and keep the common denominator. And if we distribute that 2kh, we got 800 kh or hk, either one is fine. Minus 2k h cubed minus k h cubed, all divided by 400 minus h squared to the 1/2 power. And that's going to give us minus 3 k h cubed divided by 400 minus h squared to the 1/2 power. We know that that equals 0 when h equals this value. We want to factor that if possible. We can factor out the hk, and then we had 800 minus 3 h squared here, all divided by this 400 minus h squared to the 1/2. And On the interval of interest from 0 to 20, let's look at that, those factors on the interval from 0 to 20. And our 20 root 6 divided by 3 is actually about 16. So that's on the interval as well. HK is always positive. And then this term is always positive because we're taking a positive square root of an expression that's always positive. So the only thing that might change signs at this H value is this expression. Well, you just have to determine where or whether this expression is positive or negative to the left and right of that 16.3 number. So I would just plug in like H equals 1. H equals 1, we got 800 minus 3, which is definitely positive. And then over here, this is H equals 16.3. So we could plug in H equals, let's say 19. I don't actually know what that is. 800 minus 3 times 19 squared. Well, 800 is that's 2 times 400, right? So 2 times 20 squared. That's not helping me. But if we find what that value is, we can use the sign of that value to give us this sign right here. Hopefully it's negative, but I don't actually know off the top of my head. Well, it's 2 times 20 squared minus 3 times 19 squared. I think it is less than 0. I don't actually know what it is if it's less than 0. So our function goes from increasing to having a 0 slope to decreasing. So we must have a relative max there at 20 times the square root of 6 divided by 3. So H is equal to approximately 16.3 inches. And the corresponding W value is the square root of 400 minus H squared. So I've got the square root of 400 minus this 20 square root of 6 divided by 3 squared. So we're going to have 400 times 9 divided by 9 minus 400 times 6 divided by 9, all under one radical. That's going to give us 400 times 3 divided by 9. And that's going to be 20 square roots of 3 divided by 3 as the corresponding W value. So that H value corresponds to a relative max. So we know our function is maximized at H equals 20 times the square root of 6 divided by 3 inches, or approximately 16.3 inches. And the dimensions that maximize that strength are H inches by W inches. So that's going to be 16.3 inches by this 20 times the square root of 3 divided by 3 inches. And I don't know what that is, but we can use a calculator to approximate that. So let's look at the graph on Desmos.com and make sure that, and find out what that number is, and make sure that our graph is consistent with all of the work that we've done here. Okay, so we wrote our S as a function of H, and it was K times H squared times the square root of 400 minus H squared. To simplify things, I let my K equal 1. So I'm assuming that this strength is positive. I don't know what the units would be, but H is the height of that beam in some number of inches. Now the domain of interest is 0 to 20. Because we know our height, or the height of the beam has to be greater than 0, and it also has to be less than the diameter of the log that we're cutting it from, the log that we're cutting the beam from, which is 20 inches. So we're on this part of this function, and the question is, well, where is that function optimized? Where is it maximized? I want to maximize the strength. So to do that, what we did was we computed the derivative. We did that by hand. Then we set the derivative equal to 0 and we solved for H. Now, when I graph the entire derivative, it looks like this. It's this white curve here, but we're only interested in that part where H is between 0 and 20. So that's the part of interest. Now, when we set S prime equal to 0 and solve, we get this X value. Oops, not that one, 16.33 inches for H. We can sort of see it on the graph itself. Or if we wanted to, we could actually just graph the vertical line x equals that value, and we can see that the derivative is 0 there, and then it also crosses at the maximum value of the function. And then the decimal approximation is the 16.32299 and so on of that exact answer. So we set the derivative equal, we found the derivative, we set the derivative equal to 0, and we solved for h, and we found that h value. And if we just look at the derivative graph, we see that the function or the derivative goes from positive to 0 to negative. So that means the original function goes from increasing to having a 0 slope to decreasing. So that means our function is has a relative maximum at that location, which is what we want. We were trying to maximize the strength. But the question said, let's look at the question again. It says, what are the dimensions of the strongest beam that can be cut from a round log of diameter 20 inches? Well, that's going to be a height and a width. Well, once we know that the height is 20 times the square root of 6 divided by 3, we can solve for the width. The width is the square root of 400 minus that height. So it's going to be 20 times the square root of 6, all divided by 3. We square that, and we get a width of 11.5 inches approximately. So we'll answer the question. The strength of the beam is maximized when its dimensions, let's say, are 16.3 inches by 11.5 inches. Now, this is the second method that we use, the second function that we optimize. And this function actually has kind of a cool graph because it's got that square root of a quadratic function. I really like this one because it looks neat. But we were able to find the solution to this problem using a different graph as well. Rather than finding the strength as a function of h, in the last video, we found the strength as a function of width. So we can look at that now. Just want to show you. And here we use that quadratic function, or not quadratic, that cubic function, the cubic polynomial. We solved for the strength as a function of width. We said the optimum width is at 11.55 inches. And we said the strength is maximized when the dimensions of the beam are 11.5 inches by 16.3 inches. That was method number 1. And we found the strength in terms of W, or the width. And here we found the strength in terms of the height. And we said the dimensions of the beam are 16.3 inches by 11.5 inches. So either way, we get the same answer. Just the second problem involves a lot more work. The first problem involves differentiating a third-degree polynomial. And this one involves differentiating a product involving a polynomial and a composite function involving a radical and a polynomial with a polynomial inside. But it has a cooler graph. It gives us an opportunity to practice our chain rule and our product rule. Gives us an opportunity to do a little bit of algebra to write S prime as a single fraction and then determine the sign of S prime on various intervals. So it's a good exercise as far as the calculation and computation is concerned. But if I'm trying to solve the problem as efficiently as possible, I'd probably use method number 1 instead of method number 2. But this is still a great exercise if we want to practice differentiating a function that happens to look like this. So that's it for this video. We're going to be done with applied optimization. In the next video, we'll look at 1 or 2 of the final applications of differentiation. I think we're going to do Newton's method next, and then we'll look at linearization and increments versus differentials. I'm not sure which video we'll do next, but all of that is coming up, and then we'll be done with Unit 3.